Welcome to this explainer. Have you ever watched a baseball arc through the sky or wondered how a car's speedometer actually connects to its movement on the pavement? Well, you're actually watching complex math unfold in real time. Today, we're diving into some absolutely fascinating handwritten notes to trace the evolution of motion. We're going to start with a simple throw and build all the way up to the universal rules of calculus. It really is a profound question, right? How does math perfectly predict a thrown object? In this explainer, we're going to uncover the hidden language of physical reality. We're translating these dense, handwritten equations into the everyday actions you see all around you. By the end of this, you won't just see a ball flying through the air. You'll see the invisible geometry guiding its every single millimeter. To guide our journey, here's the game plan. First up, horizontal projectile motion. Second, the math of the parabola. Third, the general projectile case. And finally, we'll wrap up with advanced motion and calculus. We're going from the absolute simplest physical throw all the way up to advanced generalized rules. Let's get into it. Section 1. Horizontal projectile motion, the physics of a throw. Let's start with something highly relatable, like throwing an object horizontally off a cliff. This right here is the fundamental building block of understanding projectile motion. Imagine an object starting up at a specific height. Let's call it h. Now, give it a horizontal push. An initial velocity we'll call u. The second it leaves the edge, it doesn't just shoot straight out, and it definitely doesn't drop straight down. Instead, it traces this perfectly smooth, curved path downward toward the ground. It's moving forward and falling at the exact same time, creating that compound motion we call a trajectory. So here's the crucial part, the time of flight. If we look at the equation, t equals the square root of 2h over g, it reveals something deeply counterintuitive. Notice what is completely missing from this equation. That horizontal push, u, is nowhere to be found. That means your horizontal speed literally doesn't matter for airtime. Whether you drop a marble straight down or flick it off a table at 10 miles per hour, gravity and starting height are the only things dictating how long it takes to hit the ground. They'll both hit the floor at the exact same time. Crazy, right? Moving on to Section 2, Math of the Parabola, the hidden shape of reality. Let's peel back the physical layers for a second and see the pure mathematical shape hiding underneath. We know the object falls in a curve, but what exactly is that curve? This is where physics and pure math beautifully intersect. When we map out a physical trajectory, tracking the x and y coordinates of our throw over time, it perfectly mirrors the pure mathematical sketch of a parabola. By systematically substituting the time variable, we can directly link the horizontal distance to the vertical drop, and the result, it's exactly the same geometric curve. Let's actually look at the math comparing the two. By isolating the variables, we see how the physical pull of gravity and our starting velocity map perfectly onto the classic equation of a shifted parabola. Our physics equation uses gravity, g, and initial velocity, u, while the standard math formula uses abstract constants like a, alpha, and beta. Honestly, the physics equation is just the math equation wearing a physical disguise. The starting height, h, acts as our vertex shift, and that gravity-velocity ratio, that just decides how wide or narrow our parabolic curve is going to be. Okay, Section 3, the general projectile case, angling the throw. Let's see what happens when we build on this and angle our throw upwards, because let's face it, we rarely throw things perfectly horizontally in real life. By launching at an angle, let's call it theta, the physics gets a bit more complex, but immensely more useful. That initial velocity, u, actually splits into two separate, independent components. We have u cosine theta pulling horizontally, which tells us how far the object will travel across the ground, and then we have u sine theta launching it vertically, fighting against gravity to determine its height. And the wild part is, these two components act completely independently of one another. Once we've got those separate horizontal and vertical pieces, we can figure out the ultimate boundaries of our object's journey. These general formulas let us solve for precise physical extremes. We can calculate the exact maximum vertical height the object will reach before falling back down. And, maybe even more importantly, we can find the exact maximum horizontal range, meaning we know exactly where it's going to land. To ground this, our notes run through an incredibly elegant specific scenario. They calculate a maximum vertical height of exactly 136 meters. Now, because of how the formulas for height and range are structured, specifically that relationship involving velocity squared over gravity, this 136-meter vertical height yields a maximum horizontal range of exactly 272 meters.
Under these specific optimal conditions, the math dictates that the maximum horizontal distance will be perfectly, exactly, double the maximum vertical height. It's just a beautiful, clean symmetry hiding right there in the equations.
All right, final stretch, Section 4, Advanced Motion and Calculus, the ultimate tools. We are graduating from simple throws to the heavy hitters, the mathematical tools for analyzing basically any motion in the entire universe.
Think about objects moving in circles. We use vectors to describe them, where the position vector r sweeps around from the center, relying heavily on trig functions like cosines and sines to plot its exact location. But the really interesting part is the changing velocity vector v. It perfectly traces the outer edge of the circle as a tangent. At every single infinitely small moment in time, the object desperately wants to fly off in a straight line, but it's constantly being pulled back into the curve.
Now, to truly master these changing velocities, we need calculus. The notes walk through this brilliant derivation. We start with a seemingly complex velocity equation, where velocity v equals a constant b times the square root of position, x. We square both sides to clean it up, then we differentiate with respect to position. And when we rearrange those terms to solve for acceleration, something honestly kind of magical happens. The variable x completely vanishes. We are left with a perfectly constant acceleration of b squared over 2. This is the sheer power of calculus, cutting through a messy, changing velocity to find the stable, constant truth underneath.
And these abstract calculus concepts like acceleration and deceleration, they aren't just squiggles on a page. They visually translate into physical reality. Imagine a velocity time graph forming a sharp triangle, splitting the total time into two distinct phases. That upward slope, that represents constant acceleration, getting faster and faster up to a peak velocity. And the downward slope represents deceleration, slowing right back down to zero. The steepness of those slopes is exactly what we're just calculating with our derivatives.
Which brings us to one of the absolute most fundamental truths in physics. F equals dp over dt. Whether we're talking about a thrown baseball, a spinning wheel, or a car accelerating, it all fundamentally ties back to the calculus of Newton's laws. Force equals the derivative, the instantaneous rate of change of momentum over time. A push or a pull on an object is mathematically identical to how its momentum shifts from one tiny microsecond to the next.
So we've seen how a simple toss of a ball is secretly a geometric parabola and how changing speeds are just the visible shadows of calculus derivatives. It really leaves us wondering about that hidden mathematical structure perfectly orchestrating the seemingly random reality all around us. If every physical movement obeys a mathematical rule, what unseen equation is perfectly guiding your next step? Thanks for joining me on this explainer. Keep looking closely at the world around you. The math is always there, just waiting to be read.